Good afternoon, everyone. Thank you for coming. Welcome. To hear about the Gatherer API, and I added some bait, the tool that was missing in a Stream API. Everybody knows the Stream API from Java 8? Yes? Who's still running Java 8? 1, 2, 3, 4, 5. Gosh. Who's running 17? Yeah, that's something like 20%, I'd say. 21? Ah, yes, this is what I like. You know that the 24 version was released in March, right? 24? I could do something about it. 24 is a nice version. 25, we already have the early access versions of 25. That's the next LTS, so hopefully you will take it. It will be released in September. All right, so everybody should, I guess everybody knows what the Stream API is now. It's not new stuff. Java 8 is 11 years old. Yeah, that was a long time ago. Maybe you should consider doing something, those of you who are still working with this one. Maybe talk to the guys who are already running 21 and see if they, job opportunities, this kind of thing. I don't know. Maybe there are. My name is José. I work for Oracle. I do have a Twitter account, actually. It's just that I don't use it anymore. So if you interact with my Twitter account and you get answers, they won't be from me, right? I moved to Blue Sky for reasons. And I also created a QR code that will take you to a GitHub page with all the links with the work I publish on the net. So I don't need to update this slide anymore, which is just what I want. And I work also with the Java Developer Advocate at Oracle on a website called dev.java, which is a great website that you should visit if you don't know it, with plenty of documentations and reports on Java 1. That was a big conference held in March in San Francisco. We're also doing many videos on the Java YouTube channel. You can connect to. We have a Road to 21 series about all the new features of the Java 21 release, because this is the LTS and this is the release usually people are interested in. I suspect that we'll be doing a Road to 25 to be released in August or September. So if you're interested in that, you can definitely check it out. We are going to talk about the gatherers. Now, gatherers, the main big features of the JDK are described in what we call JEPs, JDK Enhancement Proposals. JEPs are not specification documents. They are documents meant to be read by normal human beings and meant to be interesting and readable. So JEP is really a document that you can definitely consider reading. You have patterns of code, implementation notes, what you should be doing, what you should not be doing, etc. So it's a very interesting document. And it was released with the JDK 24 because the Stream Gather API is an API released in March for the JDK 24. And on dev.java, there is a page about the Gather API that you can read. It has been proofread by Victor Klung, who is the guy who wrote the API. So hopefully, from a technical point of view, it's accurate. Shouldn't have too many mistakes in it. And we also made an experiment on this page. All the examples, actually, you can run them directly from within the page without leaving your browser or without having to install anything on your machine apart from the browser itself, of course. And you can also edit this code and run it again to see what it gives. And the last thing I would like to tell you before we dive in is this video, which was delivered by Victor Klung, so he's the author of the API at the last Java 1, so you can also consider watching it if you're interested in the API. Great. Now, what is a stream? Short answer, an old stuff from an old version of the JDK, which is the JDK 8 version. The Gather API is not, technically speaking, it does not depend on the Stream API. Now, it turns out that odds are that you are going to use it through streams, so you need to be aware of what a stream is. A stream connects to a source of data, and you have many sources possible, many sources of data. Usually it's an in-memory structure, a collection, a list, a set, something like that. Could be a map, actually map.entry set, so it's a set. But it can be other things, like files, for instance. You can string the lines of a text file, or regular expression. With a regular expression, you can split a text, and then all the elements will be the elements of your stream. A stream has intermediate operation. On a given stream, you can only call one other operation, whether it's an intermediate operation or a terminal operation. And it has also a single terminal operation. If you don't call a terminal operation on a stream pipeline, then nothing will be computed. I guess you all know that also. So you need to be careful with that. If in your code you have stream.map.filter and nothing after that, that's probably a bug. And that's definitely dead code, so you can delete it safely. Maybe you should ask yourself, why is this code here? Because maybe it's something missing, but it's not doing anything. Okay. The difference between a terminal operation and an intermediate operation is that an intermediate operation, which is basically a method on the stream interface, right? It returns another stream, and anything that returns something else than a stream, including void, is a terminal operation. Some example of terminal operation: reduce. Usually we don't use reduce much, but yeah, it's here. To compute the result, reduce needs to see all the elements of your stream, the stream going to produce. You have other operations like find first or find any. These terminal operations do not need to check all the elements of the stream. Well, at least not always, right? If you have find first with a predicate, the first element you find will interrupt the stream and will interrupt the consumption of elements from the source. Right? And same from excuse me, and same for find any. You have a toList method. That's a method that was not in 8. It was added later. It produces a list that is non-modifiable, so just be careful with that. And you have a collect method, which was definitely there in 8, that takes a collector as an argument. And if I mention that, it's because the collector API kind of looks like the gatherer API. Okay, collector is for terminal operation, gatherers are for intermediate operations, but the idea is actually similar. Now, collectors are great because you can create your own reduction. You have plenty of collectors available in a factory class that is called collectors. There is like between 45 and 50 methods in it, and you can compose these collectors. So if you think they're not complicated enough, you can make them even more complicated by composing them. And then you have the intermediate operations: map, filter, flat map. These are the classical ones. And you also have a map multi that was also added more recently, I think in Java 17, that is doing some kind of flat map, but without having to create intermediate streams. Sometimes you just use flat map, so you create a stream of streams and you open them to do something. But sometimes actually these intermediate streams don't really need them in your computation. All right, so if you don't need them, if you just create them to open them right after that, you can consider using map multi, which is doing the same, but without you having to build these streams. And all these are going to consume all the elements of your stream. They will not interrupt your stream, which is not the case for limit. For instance, if you say limit 5, it means that, okay, I just need 5 elements, and after that I will just stop consuming all the elements from the source of that stream. So an intermediate operation has the same feature as a terminal operation, which is an intermediate operation can interrupt a stream that is being produced. And we also have, by the way, drop while was not there in 8 neither. It's a late edition. And you have also 2 other methods, distinct and sorted, which are a little weird, because when you think about it, distinct will consume an element from the stream, ask the question, oh, have I seen this element already? And if it's not the case, it will push it. And if it's the case, it will not push it. So there is a difference in the rhythm the elements are produced to the downstream from the upstream with the distinct method. And it can't work the same in parallel. We're going to talk more about that. But when you think about it, to know that, this distinct method needs to put the element in a set. All right? But if you're in parallel, there are actually several sets. So if you want to make sure that the element was not in another set, in another thread, you need to wait for all the elements to have been consumed before starting to push the elements to the downstream. That's for the parallel distinct. It's transparent for you, but this is how the API has to be implemented. And for sorted, it's the same. You cannot produce any element until you've seen them all, right? The first element that is produced by sorted is the min element of all the elements produced by the source. But for that, you need to have seen all the elements before producing the first. So if you go sorted, it's like you've interrupted your stream, but actually you're just accumulating the objects in an internal set. And then once it's done, when the source is done producing element, then you can start pushing them in the right order. Okay? But for intermediate operation, there is no way to create your own intermediate operation. For terminal operation, you have this collect method, but for intermediate operation, you don't have any method. And that's precisely the gap that the gather API aims to fill in. All right? Now we have a gather method on the stream API that is going to take a gatherer object, and this is a way to create your own intermediate operation. Now, in a stream API, along with it, you also have another API called the splitterator API. I don't know if any of you are familiar with this API, the splitterator API? Oh, yes, some of you. So you can do many things with splitterators. It's a little complex. Who thinks that the splitterator API is simple? Yeah, no one. This is what I suspected. Plus, there is some kind of trap, because you have this try advanced method that takes a consumer, but you can only call this consumer once. You cannot call it twice, which makes the API a little hard to use. Okay? Gather API kind of does the same, does more things, and it's simpler to use. So what is the gather API? What does it give you? It gives you several elements. The first element is an interface. Actually, there are other interfaces, and we're going to see them. But yeah, that's one of the entry points of the API. It's called the gather interface, and it has three types, three parameters, type parameters, just like the collector API, collector interface, by the way. And there is an intermediate method on the stream API called gather that takes a gatherer as a parameter. Okay, simple, yes. And there is a factory class also called gatherers with an S. And in this factory class, you have, I think it's 4 or 5 gatherers that are ready to use. Maybe more will come in the future, but so far there are not that many, actually. And we're going to see them at the end of this presentation. How can you implement a gatherer? Well, for that, you need to take a look at the gatherer interface. So you have a stream. Well, we are going to call it upstream. And then you create this gatherer. And we're going to see in a minute how you can do that. Spend quite some time on it. And then this gatherer, you pass it to this gather method, and then you get another stream called the downstream. Okay, and this is the vocabulary I'm going to use. There's an upstream and there's a downstream. By the way, this upstream is itself the source of the data for the gather method, right? The stream itself can be a source of data also in this stream API. If you compare this to what the collector API is doing, you have an upstream, a collector, same type parameters. Okay, this T here, the T in the collector interface and in the gather interface, is the type of the elements of the upstream. All right. The difference is that collector, the last parameter is R, and this is the type of the object this collector is producing. Right. The result is of type R. Whereas in the gather API, R is the type of the elements you are going to push to the downstream. So the return type is stream of R instead of directly R for the collector API. But apart from that, T and R have the same role in both interfaces. The middle stuff, I just put a question mark. Actually, we don't really care about that. It's the internal state of the collector or the internal state of the gatherer that is modeled by that. It shouldn't be there in the API. It's an implementation detail that is leaking in the signature. And it's not great, but this is how it has been done. So how can you implement a gatherer? Well, it's an interface, and it turns out that this interface is a functional interface. There's only one abstract method in it, which is great because it means that you can implement it with a lambda. Do you want to do that? Well, we can try, at least. So this lambda doesn't take any argument, and it returns an integrator, which is another interface given to you by the gather API. And this integrator interface is also a functional interface. And this one is actually annotated with functional interface. And its abstract method is called integrate. Its role is basically to take an element from the upstream and to integrate it in the downstream. That's why it's called an integrator. And for that, it takes 3 elements, a state, an element, and a model of the downstream. Now, this model of the downstream is a downstream interface. It's not a stream, it's a downstream, and downstream has nothing to do with the stream interface. There's no relationship between both. Okay, so technically speaking, and we need to integrate returns of Boolean. So technically speaking, you can implement a gatherer with this beautiful lambda expression. Okay, any JavaScript developer in the room? One, come on. Okay, so we don't do that in Java, do we? Oh, come on. No, okay, repeat after me slowly. We don't do that in Java. Okay, unfortunately, we can do putting a little more clear by calling gatherer.off. That's a factory method, and you pass the integrator as a parameter. And so you can get rid of the first supplier-like syntax, all right? So now you have 3 elements, element downstream. The first element, the state, we're going to leave it aside for the moment. We're going to talk more about it in a minute. And I can use this unnamed parameter feature. Yeah, the Java 8 guys, you're not aware of that, but now we can do that in Java. Just mean that I'm not going to use this argument, which is, yeah, a way to not give a name to this variable. And all I can do is call downstream.push and pass the element to this push method. And this is basically telling I'm going to take all the elements from the upstream and push them to the downstream directly without doing anything. So it's basically a transparent gatherer. It's probably one of the simplest you can write. Okay. Unfortunately, this push method returns itself a Boolean. So I don't need to do anything because this lambda returns this Boolean without modifying it. All right. So if you just type this code and run it, it will just run. And you will just push the element to the downstream. And that's it. Okay, good. Now, we can do some things to element. For instance, we can map it. I'm going to take a mapper. The mapper is not defined here, but whatever. Apply this mapper to the element. It could be string to uppercase, for instance. And then I get a map variable, and then I can map this push this map variable, and thus changing the elements on the fly. There is something that is a little frustrating with the gather API, is that this is basically doing a mapping, right? Now, how do you usually do a mapping with the stream API? You just call map, and that's it. Don't need to create this gatherer and call some kind of gather with passing this as a parameter. That would make your code much unreadable. Right? How to read, how to understand. So don't do that. But to learn the gather API, you need to go through a series of simple examples that are actually useless because this is not what you're going to use in your application. But after a while, finally say, okay, now I get it. Now I can actually do this, and I couldn't do that with the stream API directly. Okay, so this is a way of writing a mapper in an impossible to understand way using the gather API. By the way, you can do the same with the filtering. Okay, so that's a filter. It's even worse because there's an if else in it. Yes, I know it's useless. I agree with you. Plus, you need to decide what should I return as a Boolean. Okay. Should I return true or should I return false? Who votes for true? Okay, who votes for false? All right, so the right answer is true. Sorry. When you don't know, you should return true by default. That's your safest best bet. And I'm going to explain you why. How is this Boolean used by the API? Okay. I haven't told you yet, but I'm going to tell you now because this is important. And by the way, I'm not going to tell you now. I'm going to tell you in a minute. The biggest difference with the splitterator API, for those of you who remember that, the splitterator API, you can only push one element at a time. When you get this consumer, you cannot call it more than once. If you do that, that's a bug. And your splitterator will not work in all in any circumstance. With the gather API, this downstream, you can push as many elements you want to it, which is better. So in that case, we pushed one element with the mapper, 0 or 1 element with the filter, but with the flat mapping, you could push 1 to n elements. When you call the downstream.push, you get a Boolean, and this Boolean can be true or false, as usually Booleans do. If it's true, it means that the downstream is telling you, I'm okay to get more elements. And if it's false, the downstream is telling you, I'm not going to accept any more elements. If you push more elements to me, I'm not going to do anything with them. All right? Think about a limit, for instance. You have limit 5 as a downstream. Okay, so you're pushing elements. The 5 first element will be okay. And then starting to the 6, your downstream will not accept anymore. Well, it will not do anything more with these elements. It's going to throw them away. So this is the way the downstream is telling you, I'm done accepting elements. Now, if you're still pushing elements to a downstream that is not accepting them anymore, nothing will happen. You're just losing performance, but you will not get any exception whatsoever, which is probably better. This is the reason why, because your integrator should follow this rule. Right? If you're creating a gatherer that is limiting the elements, and you know that you're not going to accept any more elements, then you should return false at some point. But returning false means that I'm done accepting elements, which was not the case for the filtering. You don't want to push this element, but you still want to get to see more elements. If you return false, the upstream will not push any more elements to you. Okay? So by default, you should return true. Pushing to a rejecting downstream does not throw an exception, which is better, because, yeah, not sure that everybody will do that. Okay, so if you're integrator, you have 2 types of integrator. Just as you have 2 types of intermediate operation. You have intermediate operation that can interrupt your stream, like limit or drop while or take while, sorry. And you have intermediate operation that don't do that. All right. So if your gatherer is just transmitting the value that it gets from the downstream.push, or returns true itself, never choose to return false, then it is called a greedy integrator. All right. That's the vocabulary of the gather API, and you can signal the API that your integrator is a greedy integrator by calling integrator of greedy instead of integrator.off. All right. By default, the integrator you create is non-greedy, and you can choose, you can opt in to create a greedy integrator. If you create if your integrator is inherently greedy, but you don't declare it as greedy, it's okay. Nothing will happen. You will lose some possible optimizations, but your stream will work correctly. If you pass an integrator that is not greedy, and you declare it as greedy, then the result might be unexpected. Well, you can have a result that is not the right one. So you just need to be aware of that. You just need to be careful with that. Okay. By default, what you can do is just create non-greedy integrators. And once everything is working properly, you can just check what you've done. And if you feel like doing that, decide to make it greedy. But if you're not sure, maybe a second pair of eyes would be wise on this code. Because it's basically by watching the code that you can see if an integrator is greedy or not. Good. Just for those of you who know the split operator API, actually, if you have a greedy operator, you can call for each remaining instead of try advance. And you have one less test in your implementation, so you have a code that is faster. Not by much, but still. All right, what about the rejecting downstream? Downstream is something that is holding a state, and this state is called rejecting. So a rejecting downstream is a downstream that returned false at some point. I'm not accepting any more element. What you need to know with the downstream is that it actually acts as a door. You can see that as a door. All right? When you get a new downstream, this door is always open, and because the Boolean is called rejecting, it means that the rejecting is false. so it's non-rejecting. Non-injecting means accepting. Okay, double negation. Maybe it's not the greatest way of doing things. Okay, so the door starts, it's always open when you get a new downstream. The second rule is that it cannot commute from false to true. That is, once the door has been closed, it cannot open again. Okay? And the third rule, and it's light gray, and it's not a bug, and I'll tell you why. It can only commute, so the door can only close, can only close, because it cannot open again, on a call to push. It cannot be closed on itself, magically, between two calls to push. Okay? Now, this is not entirely true, because you could imagine creating a gatherer that would react on a clock, for instance, and that could decide to switch the rejecting state of itself on this clock that is not on a call to its integrator. And that would break rule 3. This is possible to do that, but it turns out that in the JDK you don't have any gatherer that is behaving like that. Okay, so you can assume that the rule 3 holds as long as you don't write some code that will break yourself, that will break this rule, or use a third-party library that would break this rule. Okay. And there is also a corollary, and we're going to talk more about that in a minute. A downstream is not a thread-safe object. Well, we don't care. Well, it depends. Maybe we do sometimes, who knows. So there is a isRejecting method on a downstream object. Should you call this isRejecting method? Okay. For the mapper that we just wrote, maybe we could see that as an optimization of first checking if the downstream is accepting or not, rejecting or not, and then if it's rejecting, not calling the return, right? Well, you need to have these 3 rules in mind when you want to think about that, because actually it's not. It's not worth it. Okay? When you call for the first time, the door is open, so you need to call push, and you push the element, and it will be accepted or rejected, but you don't know it until you've actually pushed it. And then you call push, and push can either return true or false. If it returns true, it means that you also return true to the upstream, so the upstream will push an element to you, and you'll get it. But because between the last call to push and the next one, there's no commutation of this state possible, actually downstream isRejecting is still false. Right? And if push return false, because you return this false, no element will come again, and your integrator will not be called. So actually, downstream isRejecting, if you call it here, it will always be false. So this piece of code is useless. Okay? When you are in an integrator, calling these 3 lines of code is useless. Don't do that. Don't do that. This is an integrator. Maybe there are other objects in which it's useful to call this code, and we're going to see an example of that in a minute. How can you push to the downstream? Well, you can push how many times as you want, just as I told you. So in the case of the flat mapper, for instance, I would happily call flat mapper apply element, a flat mapper returns a stream, right? So I've got elements is actually a stream. And then from this element stuff, I need to push all the elements to the downstream, so I could write it in that way, for each downstream column push, right? And because I need to return a Boolean, I could return true, because this is the default value. This is not very smart. There are several bad ideas in this code, and at least 2 real bugs. So bugs, bad idea. All right, so let us rewrite that. Why is it not a good idea? Because downstream.push is called several times, and maybe one of them returned false, but I didn't see that just because it's in a for each, and for each is a consumer. It just eliminate this Boolean, and I don't get it. All right, and I return true in the end, which is not that great. So we need to write a code that is a little smarter. What we really want to do is call downstream.push as long as downstream.push returns true. And if it returns false at some point, we want to stop calling it. Well, it turns out that there's a method for that, which is take while that takes a predicate. So I say, okay, I'm going to consume the element as long as the downstream is not rejecting. This is what this call is doing. And then I can call push, because I know that the downstream is accepting elements, right? And after that, instead of returning true, I could just return downstream not rejecting. Okay? And this code is probably a little better than the previous one, but I can do even better, because actually this take while and for each, following each other, is actually one method which is all match. All match will look at all the booleans that I pass as an argument, so this series of boolean downstream.push, and because it returns a boolean that can only be true if all these booleans are true, the first boolean that is false will interrupt the stream and return false. So actually this code is doing exactly the same as the previous one. Maybe it's not as readable, but yeah, it's doing the same. So now this code is less stupid, but it's still buggy. I got 2 bug fixes to go, plus 1, because actually there's also a third one. The first bug is that a stream needs to be closed. You know that, don't you? When you open a stream on a collection, you don't really need to close it, because you don't close a collection. But when you create a stream on the lines of a text file, and you don't close the stream, it doesn't close the text file. And if you open a file and never close it, what will happen after a while? Well, you will reboot your application, because the system will tell you, I can't open any more text files now, or any more files, as a matter of fact, and it will just crash your machine. So don't do that. So the first thing you need to do is that you need to put this in a try with resource statement. Okay? Now these elements will be closed when you exit the try block. Elements that close, if it's a text file, it will close the file that you opened, which is safer. I don't have any information on this flat mapper. I don't know what streams it's creating, actually. So yeah, it's important to do that. But there's also another bug here. Yeah? What did I told you about this downstream object? This downstream object is not thread safe. All right? Now there's one principle in the stream API, which is never do any side effect on external objects. You know that? Who is doing side effects on your stream? Yeah, no one. Perfect. Oh, yes, you. Okay, we talk after the talk together. Never do that. Okay? Never do that. And what are we doing here? We are pushing to a downstream, which is an external object of the stream. It's not created as part of the stream. And why is it dangerous to make side effects on external objects? Well, the problem is that if this stream is parallel, this external object will be accessed by different threads, and if it's not thread safe, you will have race conditions in it. And the nice thing with race condition is that you cannot predict what is going to go wrong. The only thing you know is that there are things that are going to go wrong. A good race condition on a release, for instance, could create a null pointer exception on add or clear. Just check the code and you'll see that. All right, so you need to make sure that this element stream is not a parallel stream. Now, you all know that there is a parallel method on the stream API. Well, it turns out that there's also a sequential method on the stream API. Nobody ever uses this method, but it's there. And if you have a parallel stream, it will make it sequential. Okay? So just think about that. Now we've fixed the possible race condition on the downstream. But there is still one bonus bug to fix. Well, this flat mapper could return a null object, right? You never saw any null pointer exception in your application. It doesn't exist. Yeah. So actually, at some point, you probably need to protect yourself against that. What should you be doing if the element is null? Well, you're in an integrator, right? So it means you don't have any element to push to the downstream. So actually, you can do several things. Just ignore it and say, OK, I don't have any element to push to the downstream. That's OK. And I carry on with the next element that will be pushed to this integrator. But maybe it's a bug, and maybe you should just throw a null pointer exception and fix it. That's really up to you. That's an application decision, I would say. But this is actually the correct code to do a flat mapping with the gather API. Or you can call stream.flatMap and pass the flat mapper as an argument also, which is probably much simpler. Okay, well, that's it. So this downstream object, it carries a state that is rejecting, and we talked about it. It's not a thread-safe object, so you just need to be aware of that and to be careful with it, especially with parallel stream, and this is what you need to know about this downstream object. Now, there is a first parameter that we ignored so far, which is the state parameter. Remember the first one? We just didn't play with it, so probably now is the right time to do it. This state is actually an internal state that the gatherer will carry on. This state is created before any element is pushed to the integrator, so you need to provide an initializer for this internal state. All right, and it will not be changed by the gather API itself. So if you mutate the internal state of this state object precisely, you will see this mutation from one element to the other. I'm going to see an example of that. Suppose that you want to create a counter. Okay, so I'm going to create a class that wraps a long. You wouldn't use an atomic long for that, right? Who would? No one. Perfect. So now this gatherer is a sequential gatherer. I'm not using the off factory method anymore, but I'm using the off sequential factory method. Okay. The first element is just a supplier to create an instance of this counter object, and only one instance of this counter object will be created by the API, and then this counter will be passed at the state object each time the integrator is called with a new element. So you just need to increment the internal counter, and if it's lesser than the limit, then you can just return downstream.push, and if it becomes greater than the limit, what should you return? True? False? Oh yeah, false. Because now you want to interrupt the stream. You've seen 5 elements and that's it. You don't want any more elements. Okay, so it's not the same as the filtering we saw earlier. So you definitely return false in that case. So is this integrator a greedy integrator? Well, no, because you decide to return false yourself. And that's the reason that makes it a non-greedy integrator. Now you can write it in a different way. There is a very nice feature that was added in a JDK, I can't remember which one. It's the one that added the var keyword in a language. You have this feature called non-denotable types. Okay, and here I'm using a super old feature called anonymous classes. You remember anonymous classes? Back in the days? Yeah, before lambdas. And these were the days. Okay, so here, the anonymous classes are not very, very useful now that we have lambdas. They kind of lost interest. But actually, if you create this anonymous class in that way, its real type is not object, as you may think. It's actually the type that is created for you by the compiler. And you see that because the type is never written here. It's all inferred by the compiler. And when you hear in this state object, you actually still have the real type of the object. So you can use its internal state directly within the stuff. So you don't need to create an external class to model this state object, which is great. Okay, what about we create a distinct gatherer? So now my state is wraps a set, and by the way, it could be this set itself. It's sequential, and because this object is not used in multi-thread, doesn't need to be thread safe whatsoever. If we decide to go parallel, now I add this element to the set. Okay, this add method is nice because if it returns true, it means that the element was added to the set, meaning that it was not in a set previously. So it's a new element. So if it's a new element, I can push it. And if it's not a new element, I'm not going to push it. What should I return here? True? Yeah? False? Someone false? No. Okay, true. Perfect. Is it a greedy integrator? Yes, because it doesn't return false on itself. Perfect. That's a distinct gatherer. We could make a sorting and distinct gatherer Now it's not a hash set anymore, it's a tree set. So it will keep the elements sorted. But this is what I just told you previously, right? You cannot push any element until you've seen them all. So now the implementation is a little different. I need to add element. And because I never call push, the downstream is open during all the process and it will never close. So I return true. But then I have a problem. When can I push my object to the downstream? Because so far I haven't pushed anything. And when there is no more element coming from the upstream, this integrator is not called anymore. So I have a tree set that is full of elements that I need to push, and I can't push them from the integrator. Yeah? Everybody got that? Well, fortunately, I have a third element, which is called the finisher. And if you know a little about the collector API, there's also a finisher in the collector API. And this finisher object is called once there is no more element to be pushed from the upstream. This finisher is called once with the state, and that's fortunate because this is where my elements are, with the downstream, which is still here, but of course it doesn't take any element because there's no more element to consume. The upstream is not producing any more elements. Okay, and it does not return anything. Why? Because after that, nothing will happen. Nothing will happen. Now I'm just going to push everything with the all match, which is the same pattern as the one we saw just a few minutes ago. All right? And now you may be asking yourself, could it be worth it to call downstream is rejecting in this finisher? Maybe it could, because I'm pushing element to it. Okay. Could it be possible that the downstream was already in the rejecting state before the call of the finisher? In that case, it's not the case. In this example, it's not the case, because I didn't call push in the integrator. So I'm sure that it's not that the downstream starts in the open state, right? But if your integrator is actually pushing elements to the downstream, it could be useful to call actually this is rejecting before trying to continue pushing to it. So far, we have three elements to the gatherer. The first element is the initializer to play with an internal mutable state. Second element is the integrator that can be greedy, and I guess you understood what a greedy integrator was. And the finisher to push elements after you're done. All right. Now, this finisher, if you provide a finisher, it will be called even if you don't have an internal mutable state. So if you want to add a last element to your downstream, you can totally do that. Should you call is rejecting? So that would be the pattern. So this is not an integrator. This is a yes. In the integrator, it's useless, but in the finisher, it can be useful to do, as long as you already called pushed in your integrator. Let us talk about parallel gatherers, because so far we've created two types of gatherers with gatherer.off, and you can suppose that these were parallel gatherers, and gatherers with off sequential, and sequential probably means it's not parallel, it's sequential, sequential and parallel, they don't go along together. All right. Well, the fact is gatherers support parallel streams, fortunately, and both parallel and sequential gatherers can be called in parallel streams. Of course, there are limitations to them, and we're going to see that in a minute. What about the internal mutable state? I told you that there is only one instance of the internal mutable state that is created in a case of sequential gatherers. Well, it turns out that it's also the case for parallel gatherers, but you have one instance of the internal mutable state per thread. Okay? So you don't need to bother having an internal mutable state that is thread safe, because this state will not be shared between threads. So having a hash set, having a counter with just a long in it is just fine. This is what you should be doing, by the way. In a parallel stream, each thread creates its own instance of your state. This is how it's working. So if you're on a regular parallel stream with 10 threads, then you will have 10 instances of your internal mutable state. So it means that at the end of the day, you will need to combine these partial mutable states into one to carry on with your computation. This is what you should be doing with a distinct gatherer, for instance. You will have 5 sets, and at the end of the day, you need to add them all in the same set to make sure that you have distinct elements. And for that, you need to provide a combiner. And by the way, in the collector API, you also have a combiner. And a combiner just takes 2 instances of state and returns another one. Or it could be the same. Okay? So how is it working? You have a thread. Your elements are being pushed to the integrator. You have this internal mutable state that is internal to the gatherer API, and you return a mutated version of that state object. If you have several threads, it will be the same, but several times, each for one thread. All right? And at the end of the day, you combine everything with a combiner, so you have only one instance of your internal mutable state with which you can play. And by the way, this is this combined version that is going to be pushed to your finisher at the end of your gatherer. Okay? Your finisher is still called only once. So for the distinct gatherer, it will work in that way. You have this hash set, doesn't need to be thread safe. All right? You have your integrator. It's being executed in different threads, so you cannot push anything until you've seen everything, because you have several sets, and you need to add them all in one set to make sure that there's no doubles in your push to your downstream. You need to pass this combiner. It's just an add all, super simple. And then you have your finisher that is the same pattern as the one we saw. So you see, going from a sequential gatherer to a parallel gatherer, regular gatherer, may have you change your algorithm in some cases, just because it is being executed in parallel. Sequential gatherers cannot be called in different threads. They can only be called in one thread at the same time. They do not have a combiner because they don't need it. There's only one instance of their internal mutable state, so you don't need a combiner to combine this single instance, of course. But they can still be used in parallel. How is it going to work? You have your source of data, a parallel stream, so your computation will be divided, spread among as many streams, as many threads as you have. All right? And then at some point, you have a sequential gatherer that needs to be called. So it means that all these threads are going to reconcile their data into one thread, call your sequential gatherer in a monothread environment, and then once the finisher is called and everything is pushed to the downstream, by the way, maybe there's no finisher, never mind, the downstream will carry on its computation among several threads. Okay? And this is new. This is new in the Stream API. You couldn't do that in the Stream API previously. All this management is completely transparent to you. You don't need to take care of everything because there is this nifty piece of work called the function framework that will do that for you. Okay, so it's completely transparent. Your sequential gatherer is executed in a single thread, but it can still jump from one thread to the other. And you can actually observe that. If you want to deep dive on this, I recommend this GitHub repository by Sven Voltman, who actually wrote some code that visually shows you what thread, well, where is your stream being computed, in what thread your stream is being computed. I'm going to go quite quickly through the gatherers factory class. So if you have several ready-to-use gatherers, a Windows fix, which is just doing that. So it just takes portion of your stream and return them in lists. Okay, you have a Windows sliding stream, which is basically doing the same, but instead of splitting your stream, you just slide a window on it. You have a scan gatherer that does that. You have a fold gatherer that is also doing this kind of thing. Okay. All right. And you have a map concurrent gatherer, which is actually quite interesting. It will execute your mapping. It's useful for non-parallel stream. It will execute your mapping in virtual threads Each mapping will be executed in its own virtual threads, and you pass a max concurrency parameter to limit this number of virtual threads. So it means that in a sequential stream, you can actually have some parallel computations, as long as it's a mapping. So in a nutshell, a gatherer is built on an initializer, an integrator, a combiner, a finisher. That's 4 elements. You have only 3 for the collectors, so that's better. Maybe a little more complex also. You can decide to work in parallel or not, even if you are in a sequential stream or a parallel stream, which is really great. Your sequential gatherer can still work in a parallel stream, and can still get benefits from that. And you can compute mappings in parallel. And this is what I wanted to talk to you about gatherers today. I think we're a little short for questions. No one is here. Okay, one question. Nobody told no. Any question? Yeah. So could you use a thread-safe state among in the integrator? Yes, you can, but you will pay the price of thread safety where you don't need it. So I don't think it's a good idea. I don't think it's a good idea. If you have more questions, I'll be hanging out at the Oracle booth, okay? Because I work for Oracle. If you feel like putting 5 stars, you can definitely use this QR code. Thank you for your attention.